The physics of the electric dipole field. The electric dipole is a measure of the separation of positive and negative charges. Stated differently, it's the system's overall polarity. Usually, this separation is extremely small. And it's much smaller than the diameter of an atom. So the way we start to think about the, di- the dipole value is about the separation. So in other words, if I have a positive charge here, and we've caused a shift in the charge orientation, and I have a negative charge that's close by where there's another one that's farther, so here you're seeing that the separation between these, which is little d, and this separation here is a larger d. And so what you're seeing here is that if we start to compare them, it turns out that a smaller separation leads to a smaller dipole value. If I have a larger separation, then that leads to a larger dipole value. Now, technically, the dipole value is called the dipole moment. The reason why it's called a dipole moment because it's part of what is called a multiple pole expansion. The first term being a monopole moment, which signifies a single charge, while the second term is called the dipole moment, which contains two charges, and it goes on. In this course, that is beyond the scope of what we're trying to do, so we don't care about that. So we're just going to focus on the dipole. And so by definition, the dipole moment E is defined as follows. So we say that we have a dipole moment, and this dipole moment is equal to the charge times the separation distance between the two charges. So symbolically, it's written as P, it's a vector, the value of the charge times the separation. So there's our definition of the dipole. So if I look at the units then read that I have a unit of a dipole moment, which is equal to a unit of charge, a unit of distance, so therefore it's a Coulomb meter. So the question is, how do we get dipoles? And this is what we talked about in chapter 1, but let's just briefly talk about this. So we start with a neutral atom that is polarized, where only a partial portion of the charge causes the shift in the center of charge locations. And what you're finding here is that the direction at first appears odd. So what do I mean here? So this is what I'm thinking. I have a charged rod, and I have in this case, let's say it's a positively charged rod. In other words, I removed electrons, and then I have my atom. So when I look at my atom, we're seeing here that the green here represents the electron. The red here represents the nuclei, and that rod then causes a shift where we now get a dipole. So as we get this dipole, we get an asymmetric atom now. So where the center now of charges have shifted. So this will be negative and positive. So the direction of the dipole moment is like this here. It says here that the dipole moment moves from the negative to the positive, while the field, the dipole field, goes the opposite direction. It goes the opposite direction. Now, before we get into more details, I want to say here is that this separation of center of charges is extremely small. And to give you a sense of this, water molecules have an unusual large dipole because their separations of charge is large. And it's big enough that what we say here is that this is about 1/10 of a nanometer, which is equal to 10 to the minus 10 meters. That's the diameter of a hydrogen atom. So that turns out to be quite large. So if I'm looking at H2O, then what it's saying here is that if I have a water molecule, I'm going to say that this is oxygen. Okay, so this is my oxygen molecule. And then I have my two hydrogens right here. And so what you're going to see here is that the two hydrogens, which are neutral, there's a shift between these two, and then there's the negative. So if I look at the shift from the positive to the negative, that distance is about a tenth of a nanometer, which is the reason why it has such a large dipole moment. But it's still a tiny number because the charge separation is so small. There are two pictures of the dipole. One is called the theoretical dipole. And the reason why it's called theoretical, because you can actually see the separations. So if I look at this thing, I'm going to have a positive charge here. And then I'm going to have the negative charge over here. And so you can actually see the separation. So what is the direction of the dipole field? So note, I'm going to draw only half the picture for time's sake. So the field, there's a superposition of the field, and then you start to see the fringing. And you're seeing here that the field is doing this type of thing. And then it looks like through the superposition here, it has a tendency to be coming in like this. And that's the direction of the field. So when you're looking at this thing, look at what you're seeing here. That right there is the direction of the dipole. We're saying here is that this is the direction of the dipole moment. It is opposite of the dipole field between the two charges. Now what happens here is that the separation distance from far away gets really small. So when I start to look at this thing from far away, and by the way, far away doesn't mean that it's going to be, infinitely far. We're just talking for dipoles, it's not that far. So what you're seeing here is that you can't see the separation. So there is a green charge, there is the red charge, but we can't see that separation. So we see the dipole moment. We can't see the dipole field here. And so then what you're seeing here is that, yes, superposition says that the field is going out and into the physical dipole. And then I'm going to start to try to recreate that same picture effectively where it looks like this here. So what we say here, just for the sake of language, let me give myself a little bit more space here. This is what I would call a theoretical dipole. Because at some distance we can't see the separation of the charges, this is called the physical dipole. So the physical dipole is what is observed and measured. That is why the dipole's moment direction is defined as it is, because we're looking at that. So we haven't practiced much on drawing field lines, so I think we should hit it right now. Now, what I want to say here is that let's correctly draw the field lines for a dipole, since it's easy to misconstrue it as I have already strongly stated, right? As I've strongly already stated, there is no flow of field lines. Even though the sketch might appear to give you that impression, that is not what is happening. So what I'd like to do here is say that what matters most in sketching fields is superposition. Of fields that dictate the field direction. So what I'm going to do here is that I want to look at the dipole field, and I'm only going to look at a piece of the dipole. So in fact, I'm going to come over here and I'm going to copy this guy right here, and then I'm going to modify it a little bit. Okay, so I'm going to look at this guy here. And again, I'm only going to look at one of the field lines, or three of the field lines. So let's start labeling the points. So let's say that right here, this is point 1. And then I'll go, this is 2, this is 3, this is 4, this is 5, and let's say that this is 6. So if I label these points, let's get rid of this stuff. I'm going to call this point again 1, 2, 3, 4, 5, and then I'll call this 6. So now what I want to do here is that I want to now look at superposition. And superposition effectively tells us that we have vector addition. So in other words, I'm going to redraw this, but try to make it farther apart so it's easier to see. So this will be my negative, this will be my positive. And when I look at the field line, I'm seeing that the field line is along these points. And then that single field line is going something like this here. So let's look at point 1. So if I look at point 1, note that there are two fields. So some people would say that the green field is coming from the positive. It's not. It starts at the green charge and it goes out. And actually, I want to try to scale these just a tiny bit better. So I'm going to say that this is a smaller green field. And then this guy here, I'm going to have a red field because they're coming from the charges. So if I do a superposition, that tells me that this is the direction of the field at point 1. So I'm seeing that the green and the red are adding up. So now let's look at 2. So if I look at charge 2, now the scaling is going to be a bit odd. But look at the red field. The red field, because it's closer, or the red charge is closer than the green one, I expect that this has to have, it's got to be in a straight line. It's going to be a larger field. But the green here, because it's farther away, is going to be a smaller field. So if I was to do superposition of these guys, I'm going to say that the field right here, oops, that does not look right. Looks like it might be going about right there. So that would be the field of E2. So when I look at the field of 3 here, you could see here is that the red is pushing the positive test charge away. The green is pulling it towards that. And so if the angles are the same here, you're going to see that these fields are then going to look like this. And that's going to be the field at 3. And so if I pick this point right here, again, the green has to be larger because it's closer. So it's got to go straight towards this guy. But then the red has to be pushing it away, but it's only pushing it away by a tiny amount. And as a consequence, I'm going to have a field that goes something like this, and that's going to be the point of 4. Once again, if I look at point 5 here, I see two fields. It's closer to the green, so the green should be larger. It's farther away from the red, so the red should be smaller. So that's going to give me a field then that's going to be in this direction right here. That's going to be E5. So if I look at this point over here, which is 6, what am I seeing? It's closer to the red. So if it's closer to the red, I'm seeing a larger red field and a smaller green field, so that the net field here is going about like that. And you could see that I can get all of these directions. Now I'd have to adjust, the lengths of these things, but I'm doing this by hand. But that's superposition. So even if it appears that the source of the field starts with the positive charge and ends with the negative charge, that's not correct. Let me say that again. It appears that all of the field lines are coming from the positive and ending on the green. That is not correct. Even if it appears that all the field lines start, on the red positive charge and end on the green negative charge. This is not correct. Both charges have fields that start at the charge and point outwards. There is no negative charge pointing in. Excuse me. There is no negative field pointing in. It's propagating out there. And sometimes you'll see that the image would say that, oh, the positive charge is like a water faucet. It's a source. And what does it do? Well, the negative charge acts like a sink, suggesting that the field line flow. That's not correct. That is not correct. Let's do this one more time. Suppose we draw two like charges interacting. So then if I'm seeing this, then we could imagine that we have, let's say, two positive charges. So I'm going to say that here's my positive charge. Then I'm going to say that here's another positive charge. And I could say the exact same thing over here. I have two negative charges, and and they're interacting with each other. And when I'm looking at this, if I start to use superposition here, when I look at the field lines, it looks like they are pushing off on each other. Right? And then they start to sort of like move away, sort of something like this. And then the same thing happens with this guy. They're going out, and then I'm starting to see the fields do something like this. Now note that I'm not being super careful, but there's a reason to this madness, and I can do the exact same thing. In fact, I'm just going to copy this because the negative charges are exactly the same thing. So what's the difference between them? The difference is, of course, that we don't have positive charges. We have negative charges. So when I'm looking at these negative charges, we are seeing that they have the same behavior, except that the arrows do not point outwards, right? They don't point outwards, they point inwards. So if I look at these guys, the only thing I have to change here now is just the direction of the field here. So when I'm looking at this, the fields look like they're coming in from infinity. They're not. They're not coming out from infinity. They start at the charges. So, for example, let's pick a point. Let's say that I pick a point right here. And let's say that I call this charge number 1, and I call this charge number 2. So when you look at the field lines, it looks like the field lines, it looks like the appearance of the field lines appear to be repelling slash blocking slash interfering, whatever language you want to do here. It looks like, because they look like they're pushing off each other, that at this point right here, that you're getting some of that behavior. The answer is that no blocking, interference, repelling is occurring, but superposition dictates the field. No. So I would say is absolutely incorrect. Once the field lines are established, the lines are static and follow superposition. But you'll hear people say sometimes that they go like, "Oh, it's blocking them, it's interfering." That's hogwash. Another thing that I should really say here is that when you're looking at these field lines, these are not coming from infinity. The field lines start at the charge and point outwards. That's what we mean by that. So just one last thing here. Let's continue with the dipole field. And so now I'm going to say the physics of the dipole. So I know that I labeled the start of this, but we didn't really talk about the dipole field so much. We talked about just sort of like setting up what do these things mean and sort of like basic definitions. But now we want to look at the basic physics of this. So the question is, what is the physics of the dipole field? One way to start is to compare the point charge and dipole fields. And one of the things that I think is super interesting is that a point charge has a net charge. A dipole does not, yet they both have electric fields, which I think is super, super interesting. So, once again, a point charge has a net charge, while a dipole does not. Therefore, they both must have different electric fields. Their fields must be unique. So now let's look at what we would expect. So I'm going to start off with the point charge right here. And what I'm going to do here is that I'm going to look at a point P right here. Okay, this is my point P. So that means I want to look at this guy. So remember, this charge is Q. And so when I'm looking at this, I'm going to say that the distance between the point charge and our observation point P is going to be Z. Now, what happens if I have a physical dipole? If I have a physical dipole, what I'm seeing is that I'm seeing something like this, where I have a dipole moment that's going like that. But a dipole moment has a net charge of 0. So if I'm looking at this thing, this is going to be the point P. Now let's draw the fields. So if I look at a point charge, I'm going to have a field line that's going to go like this. Let's say then it starts to spread out, but it's symmetric and it's doing something like this here. But if I look at a dipole field, what's actually really happening? The fields are wrapping around, and as they wrap around and they get to the point P, you can see here that the field density, the line density at point P has less lines. In other words, the point field has more lines, which then tells you it has a stronger field strength. The dipole field has less lines, therefore it must have a weaker field strength at point P. So the only thing we can conclude here is that if the point charge or the point P, our observation, moves far from each charge distribution, there is a clear difference. Now remember, we have to see a physical dipole, so we have to be far enough away that it's just a point. So then I'm going to say here is that if I look at the E field of a point, then I'm going to see here that as Z gets large, this guy should be larger than the E field of a dipole as Z also gets large. This turns out to be a very important observation because now we are building intuition. So as we go to calculate this thing, we say here is that our mathematical calculation of the E dipole field equation must match this physical, intuitive observation or assessment.